Today we have my friend Remy. He's a recent UW or University of Washington graduate in databases and programming languages. He's an expert at both, of course, and he is now at the Berkeley, what is it called?
Simon's Institute.
Simons Institute for um, workshops and things like that. And he's also about to join as a professor at UCLA. So, welcome, Remy. Very excited to talk to you about databases and programming languages and why databases are the best.
Thanks for the intro. I'm really happy to be here.
Do you have anything to add that I missed?
That's a question for you, Remy.
Yeah,
Oh, anything to add to what?
that I missed
Oh,
to
something
intro.
you missed. No, that's a really good summary.
Okay, so I'd like to start off with just a quick question. Remy, what is a database and why are they so important?
Yeah, it's a really well. The first part of the question is really tricky because uh, I've seen people claiming a fridge is a database. So, what is a database depending on what you view as data? In the most general sense, data is anything that can contains information, right? So if you have a tomato, it contains information. It's got a lot of information because it's got DNA, which can store terabytes, if not thousands of terabytes. I don't even know the capacity of DNA storage, which is a big research at UW. But if you look at a tomato as uh, storage of information, then you can retrieve the tomato from the fridge and you just interact with the database. So in the most general sense, you can look at every object or physical or abstract as database. So the way to think of it is that you can interact with this database and you can learn something you didn't learn before. So that's my most general description of databases. But practically, right, when we talk about database, we think about SQL, Postgres, SQLite, that kind of things. So it's a tool to help us organize information or digital information. And so in the early history of database, the first database was probably just a file system. So you have a bunch of files organized in a hierarchy, and then you traverse the file hierarchy to get the files out. Right. And then later on, there was another paradigm called the navigational database. And then this is where if you heard of COBOL or CODOSOL, so that was in the paradigm of navigational database. So they view data as organized in a network. So you have pieces of data connected to each other, and then you retrieve information by traversing these edges.
So was
Right. So
a join a thing yet at this point, or was it not a thing yet?
it was not a
So
thing
like
yet.
in my mind, databases are synonymous with efficiently getting stuff out of them, and that means a join. So like you're approaching what I think of a database as a
That's
database.
right. Yeah.
Yeah,
So I'm approaching that modern view of databases.
right.
But I guess just one more note on the navigational database. So that actually won a Turing Award. And then the author is Charles Bachman. And then so that was one very important and popular useful way of interacting with data. And it's so important that it got a Turing Award. And then the paper to look for is called The Programmer as Navigator.
The
So
programmer
I
as
post this.
navigator.
Yeah, I'm gonna post this in the chat. So
Great,
we can,
thanks.
yeah.
Oh, you're doing our work for
I
us.
know I was literally looking it up so I could do
Yeah.
it.
Oh, I
Um,
just looked it up to find a name. So
Oh, okay.
by the way. Yeah.
And so
so
what's next? Did we go
I,
straight from
I
that to real databases? Sorry, right.
I guess I had a question before we jumped into real databases. Like you said, the important thing or one of the important things, I think you said this, Oliver, is that like how you extract data efficiently out of databases. Well,
Yep.
like if you store your data in the program, right, then you can also extract it efficiently. So why do we need this like separate thing that sits on the side? And yes, I'm asking this question a little facetiously, but like I think it would
Yeah.
be interesting and important to like talk about why we have a category of things separate from just like data structures and programs that is
Right.
used to store data, right? What is different about the data in a program versus like something
Yeah.
like a database, and should I think of it differently in any useful way?
Yeah, so why don't we just store the data in a variable and then call it a day, right? A Python variable and call it a day. So one reason I think one way to approach that is we look at the kind of modern view of transactional databases slash analytic databases. So I'll start with the transactional databases. So transaction databases, think of it as you're shopping online, maybe eBay, Amazon, right? Or you're kind of retrieving, depositing money or withdrawing money with a bank, online bank, right? So you're interacting with this online entity that stores your data. So for the example of online shops, they store what order you placed, when you place it, did you pay, or which shipping method you picked, right? Um, so they need to do, so you need to do this with maybe a couple of online shops, but eBay or Amazon, they need to do this with millions of customers. So suppose that they have one single Python or one single binary that just keeps running, and it kind of takes orders, put it in the variables, and then process the order, and then notify the shipping department that they received the order. What might happen is that this program might crash. It can be due to multiple reasons. There might be a bug. You might run into power outage. There might be a hardware fault. And then when this program crashes, you lose all of your customer data, right? So now maybe you owe people money, people owe you money. That's gonna get messy. So one reason we need a database is that we need a way to securely store and manage these transactions or the data from the transactions. And then this takes care of what I just mentioned. It's called fault tolerance. So what happens if something goes wrong? Consistency. So suppose that your solution to fault tolerance is that you make multiple copies of the data, right? How do you make sure that those copies are consistent? Yeah, so I guess a popular acronym is ACID in databases, right? So it's atomicity, consistency, isolation, and D. I actually forgot what it is. And any,
Cool.
I guess what?
Yeah, databases people have
D
their
stands for
title games
database.
and
Durability,
acronym
durability.
games on point, right? We've already
Yeah,
seen
yeah, yeah.
title for a paper and also some acronyms. So I guess to distill down, well, I guess the acronym distills it down for you, but some of the keywords I heard here was like initially maybe people were trying to I don't actually know if I'm curious if you know the history of the separation. Does it come from the fact that you want persistency of your data first? And that's why people started storing things in file systems, and eventually it evolved into some more structured form of a program that we now would recognize as a database.
Yeah, so these are all real problems. And then, if we look at the technology, we had disks for the longest time, right? So it was kind of easy to provide the persistence. And then, so the D in as it actually stands for durability. So that's slightly different from persistence. Think of it as, persistence on steroids. Right? Durability means that no matter what happens, the data is still available, right? So to achieve that, you might want to make multiple copies, even if the hard drive uh, kind of gets
Right,
corrupted. You can
right.
find it somewhere else. Yeah.
Right, because one definition of persistency is actually like your program crashes, but your system is still functioning. Your computer, like your physical computer where you've located it, it's still working. And so
Correct.
you have
Yeah.
persistency, but you only really have persistency as long as you have that computer. If that computer
Yes.
were to crash or get destroyed for some other reason, you lose that data. And so durability is one step above the idea of persistency because it's trying to say, even if that one computer dies, my data is still alive because I've sort of replicated it over many different machines and many different geographic areas, maybe, or something like that.
So just
Yeah, yeah,
to
that's
just
the
to
way to look
tie
at
it
it.
back to our original question, we could roll our own data structures and do a bunch of crazy stuff. But in my
Hmm.
mind, the problems of databases like atomicity, durability, and like all of the like scaling to lots of data are so hard that there's like a whole field for it and you don't want to roll your own. And you also need an
Exactly.
interface for using the database that other people have written so you don't have to roll your own. And that's
Yeah,
like what we
precisely.
call a database. Like that interface is the database. You can implement it many different ways, but like a database provides that interface, I guess.
Yeah. So database is software. So if you are going to make a software that provides asset guarantees plus other things we haven't talked about, you will be building a database.
Right.
So that's kind of by definition. Right. So we talk about a lot about transaction. I don't want to ignore
Oh
analytics
yeah.
because that's where my true heart is. I actually never worked on transactions to the date. So for analytics, so the idea is that uh, before we talk about millions of customer interacting with one single data uh, uh, kind of a data owner, right? Or people who manages data. So analytics is a slightly different model. So the user of an analytical database will be something like some analysts at the company. So for example, for eBay, maybe they have business analysts and they want to figure out, oh, we run this promotion, was it successful or not? Did it actually increase the sale? Did it bring us profit? Right, in order to make future decisions. So that's a very different mode of interaction because before each user will only touch their data related to their account. So it's kind of many interaction with the database or many transactions where each transaction only touches a small part of the database. But for analytics, for example, you want to figure out your demographics, what's the average age, then you actually have to touch a lot of the database. And then you're not going to run as many of these queries. So you only have a few analysts working maybe as day jobs. So they will be writing complex queries that touch a lot of data against this database. So it's a really different way of interaction.
Is there a is is it useful to think about this distinction as the difference between touching more rows of a database versus touching more columns? Like, is it the case that analytical queries in general will touch more rows but fewer columns in each row, whereas other queries will end up sort of touching the giant row associated with the user, but maybe not all of the columns?
Yeah,
Or
so I think if we just look at roles, analytical workload definitely touches more roles than transactional. For columns, I actually don't think there's a huge difference. Uh,
Hmm,
yeah, depending on it all depends on your query, right?
I guess like the convention is that the columns are sort of the data associated with one entity, like a user or something like that.
right.
Like you don't have to
Yeah.
use rows and columns in this way, but like traditionally we're talking about rows and columns in that with that context, right?
Mhm. Yeah. Yeah. So if your analytical query is really complicated, so it needs a lot of attributes and it needs a lot of features of product, it needs a lot of information of the user, you will have to use a lot of columns as well.
Right, exactly. And so I guess we'll get into this later on, but I assume people optimize the way they represent their data depending on what they're expecting their workload to really be, transactional versus analytical.
Yeah, exactly.
And I guess in the case that you want both, it might be tricky if you want your analytics to be like guaranteed very up to date or something like that.
That's right. Yeah.
Yeah,
So that's why there's I think a pretty growing market of the so-called hybrid HTAP, so a hybrid transactional analytical processing. So that's kind of exactly the kind of database that will support both modes of interaction. And then
what's an
another,
example of one of these that supports both modes of interaction well? Like, is SQLite out of the box good enough?
well, SQLite is really SQLite is actually a pretty special breed of databases.
Oh, I see.
So, it's designed to be embedded in other applications. So you'll even find SQLite in your car
Right.
because apparently cars need a database manage some states, maybe its knowledge about the functioning of the different parts of the car. So SQLite is a really special breed. So you could build either a transactional or analytic database with SQLite, but it's not really designed to support that kind of scale, right? So an entire SQLite database is stored in a single file,
I see.
right? So if
Okay.
you lose that file, then
So we're
you're
talking about much more serious software that's like, you know, the SQLite doesn't have the durability part across multiple machines.
right. You can add SQLite DLP to SQLite by writing a bunch of code,
Yeah,
but if you something like Postgres, then you get durability as well.
I see.
Yeah. Yeah, so I think there are a lot of pretty innovative databases trying to do HTAP. So my favorite one is actually I don't know if they advertise themselves as a HTAP database, but their approach is that you're running your transactions and as you said, our goal is to keep our analysis up to date, right? So they're in the category of streaming databases. So
Um,
basically, you can define pretty complicated operations or incremental databases, right? So they will run your analysis once, maybe take a long time, and then as new data come in, they will incrementally update the result without computing from scratch.
Interesting.
Yeah, so you can think of it as one solution, one approach to HTAP database.
Yeah. I think we're getting into some of the deeper topics, but I was curious to bring us back to a little bit of the history of databases, which you were going into.
Mm-hmm.
Right. So I'm curious, like once we sort of decided that a separate representation is useful, um, one thing I'm curious about is the design of the interfaces that people came up with when building
Mm-hmm.
databases, right? Like today, if I think of databases, SQL is the interface I think of. Like whenever I think about interacting with the database, I'm like, you use SQL. I know there are no SQL databases as well, but like SQL pretty much seems to be the dominant interface mechanism in databases today. So I'm curious what the history of that is, if you're familiar, and why it ended up being such a successful abstraction, right? Like
Yeah.
in programming languages, there's pretty much no abstraction that has that kind of a crown. Like there's no obvious right solution or like dominant way of writing programs. Maybe variables. I don't know. Variables are pretty good, but like
I like variables. I like loops
oh
too.
yeah, actually no, pure functional programming, no mutable variables. So maybe naming things like something very simple.
Yeah.
Yeah.
Okay, yeah, but getting back to databases, so yeah, it kind of it's a nice sequel to navigational databases, right? So before we had the navigational database, and then people really had to write really complicated program to get any data in or out of database. So, programmer as a navigator is kind of what you would think like, right? So they would visualize this really complex space of data in their head, and then they would say, "Oh, now I follow this link to go to that part of the hierarchy, and then go here, go there." So it's a really physical way of interacting with the data. And then for that, it's quite brittle because
Right.
sometimes you might want to change the physical representation of your data, maybe to get more efficiency. Maybe you want to change the data structure, you want to change the underlying hardware to your data. And then
Right.
sometimes you also want to change the logical representation of the data, right? So maybe before you just throw everything in a huge table or a huge hierarchy, and this hierarchy is not fixed, right? So data evolve as people and the software evolves.
Yeah,
So
the way you're describing it, it almost makes me feel like you're just at this point, pre-SQL, you're just working with programs where the data is living with
yeah.
some extra guarantees than you would have in a normal program state, but you're still fundamentally working with it
Mhm.
using programs
Yeah,
and
so
working
it's really dirty
kind of
and really physical. Yeah, really
right.
make really close to the metal.
And
Uh,
this physical word, I guess, is important because you're going to come up with
yes.
the next
Yeah.
sentence.
So the next sentence is that what underlies SQL is called the data independence. So that's the core. Well, actually, Before that, what underlies SQL is a relational model of data. And then the core feature of the relational model is data independence. So what that means is that you can write your program, which we call query in the database. So you can write your queries that interact with the database in a very high level declarative logical way without regard of the underlying physical physical structure of the data. So one concrete example is that so for example, you have some indices on data, right? So an index for a table means that you build for example a hash table on certain keys so that you can efficiently retrieve maybe I want to hash our student records, our student IDs, so that when I want the transcript of Ratchet, I can just go find this ID and then go find this hash table to get it really quickly. Right. So that's one physical representation of the student table. Right. But when we write a SQL query, we don't need to talk about this index. So index is something physical. So in the SQL query, we were just talking about, oh, I want the grade of Ratchet, go find me. And then the database will automatically translate this higher level description into whatever physical representation of data and then execute it.
So this
So
is getting very interesting because you have this very high level data independent query that you're running in like SQL or something like that. And
right.
you mentioned that there are these index things, which are some sort of cache that the user can specify.
Mhm.
And the user does have to specify what the indices are, but they don't have to say how to use them. This is something I've been thinking about recently. And so you have this really high level language, but you still have to give a hint about how to make it more performant, but you don't have to tell the database how to use that hint, like where to instantiate that hint of where to use the index. So I think that's a very interesting spot that databases found much earlier than like other systems.
Yeah, so I think there's also a important point, which is that there are different kinds of people working with the database. So as you said, there are users who write their queries and they don't want to talk about indices.
Right.
And the user who created the index doesn't have to be the same user. So in fact, it's usually what they call database administrators, right? So they hire a few people to look at what kind of queries the database is
Right.
receiving, and then they will build up these indices for the user so that all their queries run faster.
That's very interesting, like a separation of concern between the database wizards and the people who just want to write some darn queries.
Mm-hmm.
Yeah. But anyways, I may have
Just yeah,
sidetracked this a
this
little.
sort of this idea of like sorry to cut you off, Oliver. The audience might not know, but I'm on a different continent, so there is going to be lag. Apologies for that. But so this concept of like data representation independence is really interesting, and anyone who tries to write portable programs in air quotes because portable programs don't exist when you want to do performant like programming. Uh, People know that like to do that, it's really hard to decouple your data representation from how you compute on it, right? Like the
Mm-hmm.
fundamental problem of how to write high performance programs can often be how do I represent my data in the correct ways so that I can define my computation on it so that the computation is always fully utilized, my compute units are always fully utilized, and I can go from there. But fundamentally, that means you're tied to the hardware that you're working with, right? And so this idea of data independence in databases allows you to sort of find this decoupling
Mm-hmm.
that gives you the ability to write nice compositional programs. But of course, it comes at a cost, right?
Yeah.
And so I guess indices are one of these mechanisms that are essentially programmer hints or like top level optimization directives of some form, right? Um, that you give to the database, and the database is like, I know what the data inside me is. I'm going to compute some information over that data. So I'm going to compute some data about that data. I'm going to use that to optimize future queries.
Yes.
This is really interesting, right? Like again, if you come from a traditional, I write programs that run once and then exit,
Mm-hmm.
this is not how we think about our programs. We think about our programs as being optimized and their data representations being optimized by the compiler. But if
Mhm.
you live in a world where your program is persistent or some part of it is persistent, you can like look at repeated executions and learn how to optimize that better.
Yeah,
So I'm,
or when the data is persistent, right? So you know this is exactly the data you're working with. So when you run a program, you have no idea, or you have really little idea what the input is going to look at. So you need to be really general. But now most of the cases we know this is exactly the data we're going to work with, and maybe changes to it will make a little difference. But we have a much more information about the actual data than regular programming.
yeah, and so this leads me to maybe a philosophical question, which is like, do you think most programs, if written in this sort of persistency first model, can benefit from repeated optimizations, right? And so
Yeah.
here's a concrete example where like let's bring it back to compilers. The traditional model of thinking about a compiler is a bunch of like, here's my program, here's my
Hmm.
compiler, run the compiler on the program, get the
Hmm.
output, and then run the output. But that's not how we use compilers. We use compilers in our IDEs, we use them through language servers. And in that case, the compiler is running in the background repeatedly every time we edit our program. It's sort of being executed over and over, right? And
That's
so this
correct.
seems exactly like the kind of persistency that could be useful to build sort of the kinds of optimizations that database people have come up with.
Yeah. Yeah. So I think if you know there's gonna be a pattern in your workload, then of course it makes sense to try to train your program or train your compiler to cater to the workload. And I think in PL there has been approaches of doing this. So in maybe not in compiler, but in general, there's the so-called auto tuner, right? In ML, right? So you want to try a bunch of different settings and then find the best one just for the data you have. And then for PL, I think the closest thing I can think of is partial evaluation.
Mm.
So if you give me the actual exact data I'm gonna run, I'm gonna treat it as part of a program, and then I'm gonna optimize this kind of inline program just so that it runs fast on this data.
But
Yeah,
also
that's an interesting line.
build systems and compilers are sort of like what you're getting at. It's a database that keeps track of what has changed and what needs to be recompiled and what
Like
optimizations you
those
might be able to
systems are
do.
like the worst
They're
version of
like,
a data.
yeah, they're very crappy
Oh,
databases, right? And they're not aware of what the compiler is doing. They just like say, do this whole chunk, compiler. I didn't remember anything about that chunk.
yeah, but like a lot of modern compilers are actually being rewritten to support this kind of incrementality. Like the Rust compiler actually, do I want to say that? I think Rust Analyzer, which is one
Right.
of these LSP tools for Rust, is actually written in an incremental fashion. And the Rust compiler is written using this like query model that allows them to do efficient recomputation over programs as well. But it's like a post hoc re-implementation. I don't think it was designed as an incremental compiler in the first place. So I think there's growing understanding that this kind of like pervasive, persistent kind of model for compilers is also useful. But going back to databases, indices were one of the sort of, I don't want to call it obvious, but because I'm sure it wasn't obvious when people started doing databases, but like it seems pretty useful um, way to do sort of optimization over persistent data. I'm curious what other kinds of things people have come up with to do these kinds of like optimizations over persistent data
Optimizations over persistent data. Let's
or
see.
using persistent data.
Yeah, I mean, so for distributed systems, all they care about is, how to have consistent state. Or I actually know nothing about these distributed systems, aside from talking to my friends. But so maybe I should say most of what they care about is that you have some state and you want to keep it consistent, right? And then you can think of that as being maybe one layer below databases, right? So database uses state, and then you can build a database on top of some kind of distributed consistent protocol. Uh, and so basically, the research on distributed systems basically tries to figure out. Now we have this machine in Europe, this machine in this other continent, right? How do we make them talk to each other efficiently? And when one of them goes down, how do we um, how do we figure out what to do, right? So another acronym over there is a CAP, a CAP theorem or a CAP guarantee, whatever. So what people should read about it, I hope I can find it later, is some argument against CAP, right? So CAP, let me look up what
I'll
it
put
stands
in the
for.
Wikipedia. Yeah.
Yeah.
It's
Consistency,
consistency,
availability,
availability. Yeah.
partition
Adaptation,
tolerance.
right. Yeah, so the CIP theorem basically says that you can have all three. You can have consistency. Availability means that all of or your data is available. So if a customer want to find some data, they can go to somewhere to find it. Even if maybe their local data center goes down, they can go to another data center to find it. So that's consistency and availability, and then P stands for partition, network partition tolerance, right? So it basically says that if we have these data centers connected by network, and if one of them just got cut off, right, they're just in their own island, then then what do we do? Then can we still make sure that there's some way to guarantee either one of making the rest of the data consistent or making something available to the people, right? So the theorem says that you can't do the all three, and I want to look it up because it's actually a really good article. I think it's got
James
I
also
hope,
mentioned that availability means you also need to be able to write, not just read the database.
correct, yeah. So what I just posted is this article by Martin Klapman.
Oh, really?
Title please stop calling database CP or AP. Right. So the theorem says that you can either have CP or AP, you cannot have CAP,
Right.
but it's kind of arguing saying that this is a really narrow view of the database landscape. So I need to refresh my memory, but I recommend people who are interested in this topic read this article.
Neat.
Yeah, this is a really useful set of links you're posting, Remy. We should archive these and post it in the chat for people listening, the
Mhm.
recorded version of this as well.
Mhm.
So I guess we touched one of the aspects you mentioned about the dominance of SQL, which is like the data independence and why this is useful, right? The
Right.
the other thing you mentioned was the relational model, right? Um, and so we're going to talk a lot about the relational model, I'm sure, but I just want to say if they're like PL people in the chat, there's a time in the life of every PL person that they realize that databases people have just they have the most beautiful abstractions and we should give up on what we're building and just go work on the relational model. So what is the relational model and why is it so cool? And some of the questions that we've already been asked is like related to specifics about the relational model. So please teach
Mhm.
us about the gospel.
Please, Remy.
All right. Yeah, so the relational model is a data model. And then a data model specifies two things. One is that how do you abstract, what's the abstraction for data, and what's the abstraction for queries or programs over data, right? So relational model, as the name says, the abstraction for data is relations. And the abstraction for programs is actually logic. So the name we'll give it is relational calculus. So this might be the first time people have heard of relational calculus because most people have heard of relational algebra, but I actually hadn't heard about relational calculus until maybe a couple of years ago, kind of a few years into my PhD, right? So relational calculus really is, you can think of it as first order logic. So it's really logic, but it says that first of all, if you have a close sentence, it's either valid or invalid. Right? You say for all x, p of x is true, or exists x where p of x is not true. Right. So for relational calculus, you can think of it as every query as a first order logic sentence where there are some free variables. Right. So one example, I don't know if what's about, or maybe I'll type in the chat. Right. So we want to find uh okay, I'm just thinking about this on the fly. So exists y such that uh uh R of X, Y, and then S of Y, Z. Yeah, so I'm typing in chat. So this is a logical sentence in first order logic, right? So the interesting thing about this is that it has
So
two variables.
yeah,
Yeah,
just to pronounce the sentence for people who will be listening purely through the audio, I think the sentence is there exists some Y such that R relates X and Y and S relates Y and Z. So like one
yeah,
example of this could be, I don't know, people who own dogs and dogs who have leashes. I don't know.
sure,
Something
yeah.
like
Yeah, you
that.
have two
Yeah.
different relations, like of different things, but you're looking for rows in both relations where they share one of the attributes is all we're trying to
Right.
get at.
So find me every dog that has both
Yeah.
an owner and a leash.
So it's a query you could write in like SQL, but Remy is going on about this relational calculus thing, which he thinks is like the core
Yeah,
idea
that's the
behind.
mathematical foundation
Right.
for SQL. Yeah.
Right.
Right. So the query, just to make sure people understand it, the query says that, or the formula says exists Y such that R of XY, so R is a predicate over XY, and conjunction with S of YZ. Right. And then so now X is quantified by this existential variable, so it's a bound variable, whereas X and Z, they're not quantified, so they're free variable. So the way we write this in another notation called the uh, conjunct queries. I think I'm triggering some trauma for people. So please cover your eyes if you have PTSD from racial calculus. Okay, so I'm just writing down the database notation for this, and also coincidentally, this is the Prolog notation that that kind of came out of logical programming, right? So this is just one notation to write, another notation to write the same sentence. But here we're explicit saying that we want to store the output xz in the relation q.
Right. So going back to our dog owner leash example, now the query says, find me every owner leash pair such that the dog owned by the owner also has a leash. This is
So
such a
in other
terrible
words,
example.
find
Yeah,
everyone who leashes their dog, right?
exactly. Okay, much better. Yeah.
Yeah.
Okay.
And let me just make sure people who like SQL understand this. This is gonna be select person. This is a leash. I'll
In
just build.
fact, Remy
I'll
is just a compiler across various
yeah.
mathematical
I was
functions for
gonna say
database.
we've run headfirst into a classic database problem, which is like, how do we write this crap down?
Right, right. Okay, so but okay, I'll let Remy write this down, but this is for the SQL folks who might be listening to this, and then I can try to pronounce it. Um, okay. So it says select xz from rs where r dot y is equal to s dot y. So I guess it would be like select owner leash from the relation owner owns dog and dog is leashed. And then find me all of the owners such that they leash their dog.
Yeah, yeah. Find the pair owner leash such that the owner uses the leash for the dog, right?
Right, right.
Yeah, I need to prepare more less complete example for when I'm actually teaching this. But this is hopefully this is helpful.
This
Yeah,
is
this is
this is
good
fine.
training.
Yeah. Okay, so given this, we were talking about the relational calculus. So let's bring it back to that,
Yeah.
which is which one of these three sentences is the relational calculus representation of the query, the SQL query? I'm
Yeah,
assuming
so
it's
these
the
are just three different syntaxes, right? So if we just talk about pure first order logic, which is usually what people use when they talk about relational calculus, that would be the first one.
I see. Is it the case that relational calculus can be embedded in purely first order logic?
Let me think about that question.
So for background, first order logic is the logic of basic propositions and then propositions that can be quantified using the for all and the exists quantifiers. So you can say things like, for all animals, there exists some animals that are white and eat the other animal. I don't know. Is this very bad analogies today? I'm sorry. But
Yeah.
One thing
yeah,
I've always been
Um,
confused about in forced order logic is like, what is the stuff you can talk about? Is it dependent on your own first order logic like flavor?
we're going to have James Wilcox on this show one day.
Okay,
And we'll
thank you.
yeah. Uh, yeah, I'm not gonna eat James's lunch, but to answer Roger's question, so by definition, relational calculus is first order logic. Even if you don't
Oh,
have variables, then that's called a nullary relational calculus query. So either returns nothing or returns an empty tuple, right?
interesting.
Yeah. So by definition, relational calculus is first order logic.
And it's equally expressive. Like you can express arbitrary quantifier alternation
Yes.
with, okay,
Yeah.
cool.
The problem is that sometimes if you say, find me all the people more, let's see, uh, yeah, this is a little tricky to find an infinite example, right? I'm trying to find some query that returns infinite tuples. Okay, I guess find me everything that's not a person, right?
Sure.
That's a valid first order logic sentence, but there are infinitely many of things if we don't
Right.
consider ourselves to the universe. That's not a person. So you can express anything you like, but certain things can be answered, certain things cannot be answered.
So it's a
Right.
subset of first order logic?
Oh, no, no. So in relational calculus, you can express anything. I'm just saying not every relational calculus query can be answered.
Oh, I get it now. Okay.
It's
Okay.
just like not every Python program terminates. Not every relational calculus returns finite results.
I
Okay,
see.
so I guess I've driven us into the big hole of a question, which is, okay, this mathematical model is beautiful and great, but you've just pointed out that it can have potentially infinite output, right? And so bringing it back to databases, why is this model still useful? Because I assume the model over databases is fundamentally finite, right? Like when you do queries over databases, you have some set of
Right.
input to start with, and you want to do queries that will generate some output. And hopefully that output is finite. I don't
Hmm.
know. I don't know how often people compute infinite queries. And so what is the connection between the possibly infinite model and the almost definitely finite physical representation of the model in databases?
Yeah. So I think maybe I will massage the question a little bit into can we know when the program will return finite answer, when our relational calculus query will return finite answer? In general, unfortunately, this is impossible. So there are proofs showing that it is undecidable. So if you don't have your data, you can't have an algorithm just takes in a logic sentence and then says, oh, this will return finite for all inputs, or return not finite for some inputs. So there are two kind of wrinkles in this, which is that if you have the data, then it is possible there is an algorithm, or there are algorithms to determine will my query return a final result on this data. So that's kind of all we care about, right? So because we're always going to run a query on the database. So if you have the data, have the query, you will know that if it's going to return a finite number of results. So if it's infinite, you just don't run it, right?
Interesting.
Is
And
it,
And
tools
does
like
it take a
SQL.
long time to decide whether it's infinite?
so that's what research is working on. So the first proof of such an algorithm is purely theoretical. So it's highly, I don't know, doubly exponential, completely impractical
Okay, so it's super
to
impractical.
actually run. Yeah. And then some more recent paper saying that you can actually implement this algorithm on top of a database. So there
Mm.
is, you can think of it, there's a SQL query that tells if your other SQL queries will return final results.
No way.
Yeah, that's super cool. So I'm gonna try to look for that paper because it's one of my favorite database papers. Um,
Huh.
let's see.
Rad. See, this is what I mean. Relational model is the best because like your proofs about the model end up being in the model. That's not quite true, but like they can use the model
Yeah,
to do.
it has that kind of a self-referential flavor. So I
Yeah.
found this paper called Efficient Evaluation of Arbitrary Relational Calculus Queries. So arbitrary means that you can write any first-order logic. So one caveat is that you can't do math, right? You can't. So in this paper, they don't support plus, times, less than.
No
So it's
primitives, yeah.
no, no primitives. Still quite theoretical. Um,
Right.
But
uh,
so how do we deal with this problem in practice right now? Do we restrict the language so that you can't write infinite queries?
Yeah, so the practical solution is that so the example I gave you is that find all the things that are not people, that are not dogs, right? So the practical solution is that always give a finite range of anything you talk about. So instead of saying find everything that's not a dog, find everything in this house that's not a dog, right? So that's
Uh,
the let's see. Yeah, I'm missing the technical term on it. So there's an important theorem says that if you always do this to a query, then it can always be evaluated by relational algebra, which is the part people are familiar with, right? Relational algebra, you just have joins, group by projections, everything is finite, everything is efficient. So as long as you always do this to your data, you always kind of quantify everything with a finite range or a finite domain, then you can always compile it down to relational algebra.
I see. So relational calculus bad, relational algebra good.
Well, they're good and bad in different ways,
Right.
right? Relational
But like
algebra
in
is
practice, you want the relational algebra
for the machine, right? So
for the
for the
machine, yeah.
machine, they like relational algebra. They
Yeah,
have no
yeah.
idea about relational
But when
calculus.
we're thinking, we like the calculus because you have, is it negation is one of the big problems? Because you can negate
Negation
things and get
is
infinite things.
Yeah, negation is basically the problem for everything logic, right?
Right.
Okay. So before I forget, the theorem says that so the technical term for putting a range is called range restricted. So the theorem says that every range restricted relational calculus query can be evaluated, can be compiled down to relational algebra. Uh, and I
Mm,
wonder if this is the so-called Codd theorem. So Edgar F. Codd. So he's basically the guy who invented everything, who invented the relational databases. And just want to get the record straight. Yeah, it's Codd theorem. So it's a little bit more nuanced than that. Okay, so you guys already found it. So for people who are interested, read this more, right? So there's no sort of domain independence, so that's a little more subtle than is this finite or not. But yeah, that's the thing to look for.
interesting. So
Okay, we went really
when
deep.
do yeah, yeah. I guess maybe I should hold off the question, which is like when do people actually use one or the other? But I guess this is mostly relevant for people doing the deep thinking in databases and not necessarily people who are using databases day to day.
So what do you mean one or the other?
The relational algebra versus the relational calculus.
Ah, so it's actually I think a practical a question. So for people who use relational algebra, those are people who build databases because relational algebra is closer to the machine, right? So it says how do we actually run this query on my hardware? So pretty much all SQL databases they are built around some extensions of relational algebra. So every company has their own flavor of relational algebra. So database engineer, database builders, they work with relational algebra. The interface they provide to the users, which is SQL. So the root of that is relational calculus. So you can think of SQL basically as not as crazy relational calculus. You can't really have arbitrary quantifiers, uh, and so it's quite restricted. But the mathematical foundation of SQL is actually relational calculus.
I see. Interesting. And so SQL is designed in such a way that even though the foundation is relational calculus, it ends up being most of the time something that fits into a machine that executes or like a virtual machine that executes the relational algebra.
Right. Yeah.
Virtual machine being the database itself. Interesting.
The database itself. Yeah. Yeah. And then maybe a little bit far-fetched way to look at this is that the connection between relational calculus and relational algebra is Codd theorem, right? So Codd theorem said you can turn relational algebra,
Ah,
calculus into algebra.
I see. I mean, yes, makes sense. Makes sense.
Interesting.
Um, so you mentioned a couple of interesting terms when you were talking about the relational algebra. You said joins, and you mentioned the word joins several
Uh-oh.
times. The show
It's
is named
time.
TheForkJoin. We have to talk about the join, and the history of the join. And so, yeah, tell us what the join is and why do people care so much about the join algorithm? I think like in the first 5 minutes, Oliver mentioned the join algorithm, so clearly there's something there.
All right. Yeah. So why do we care? Why should you care? So this is also part of my thesis defense. And then if we look at relational algebra, so the famous operators are selection. So selection means that give me a table, give me a condition, return all the data that satisfy the condition, right?
Filter.
So find all the dogs that are older than 2 years old.
Yep.
So this is one. Projection, which is very simple. Give me a table, just return a few columns, right? Throw away other columns, maybe find, give me a owning table or ownership table or family table, like find the name of every dog. I don't care about the
Right.
owner.
So projections let you cut down on the columns.
Right. Selection
Selection
and
lets you
lexical
cut down on the
exactly.
rows.
That's a good
Right.
way of it. Group by, which is a little. I always don't like group by because it's two steps. So you first look at couple attributes of each row, and then you say that, oh, for all of the people living in the house in the same household, group them together, right? And then for each group, we're going to calculate maybe the average age or average income, etc. Right. So the reason I mentioned these before drawing is that notice all of these are single table operations. So when we
So
select
sorry,
from
sorry. One thing that was not clear to me is what is the output of a group by? Is it
right.
more columns? It is more rows, or
So it's a bunch of rows. So group by takes one table, outputs another table.
I see.
Yeah, so
I see.
that's all we care about, right? So all of these three, projection, selection, group by, they're all single table operations, which means that they can always run in linear time to the side of the table.
Right.
Whereas join, it takes multiple tables, or if you talk about the binary join, so when people talk about join, they usually talk about binary join. It takes two tables and then outputs another table. So in the worst case, if you just have two tables, it can run in time quadratic
Yeah.
to the side of the table. If you have 10 tables, it can run time, n to the 10th of the size of the table. So people care about join because, it's hard. And another problem is that it's also useful, right? So join is the only operator in relational algebra that lets you combine information from different sources. So
Right.
we're programmers, the foundation of programming is composition. So join
Yeah.
is a compositional operator for relational data.
Right. It's
So
sort of the standard PL thing of like what makes a language is primitives, the ability to compose, and the ability to abstract. I guess there's no
exactly,
ability to abstract yet.
yeah,
Maybe you need a lambda in the relational algebra to get, I don't know, abstraction. But apart from that, yeah.
yeah, yeah.
So
So
you well,
relational abstraction later. So that's actually just the set comprehension, but that's also kind of interesting.
mhm.
Just to back, so one, we can compose data together, and then two, that we can also compose queries together using the join, right? So in functional programming, we have the composition operator for function composition, right? So the little circle you say f composed with g gets you a new function. So you can also compose two queries together using the join operator. It is not how people use queries, right? So what happens is that people might write subqueries. So they will write an inner query outside of the outer secure query. And then how that actually gets executed in the database, what happens is that they will unnest these subqueries and replace them with joins. So that's
Can
a
you give
really
us an example of this? This is really interesting. I guess I've heard about the n+1 problem,
yeah.
as something that often shows up. But that usually shows up at the programming interface of the database and not necessarily when you write several queries. So how does this work? Like
Yeah, so
what kind of query would you have to write?
let me post this paper and then maybe try to pull an example from there. So should I screen share? Would that be helpful?
Oh, I think it would be easiest if you just tell us, like
Okay.
in words. I know it's annoying and hard to do, but it'd be cool.
Well, I'll try. So I'm looking at this query from the paper. So that's Q1 from the paper, and then the text description is that it's a necessary query to find for each student the best exams, right? So they want to look over the student database, the exam database, and for each student they want to see which exam they did the best in. And then the SQL query, it's not it's gonna be a disaster, but I'm gonna try. So
Okay.
it's level SQL query, and on the outside we have select student name as student course, or a select student dot name from the student table, and select exam dot course from the exam table. So we're working with two tables, right? So we are selecting from students table and exam table. And the first condition is that the student ID stored in the student table equals to the student ID stored in the exam table. So that's straightforward, right? So we just want to match a student record in the student table to the student record in the exam table, or
That's
the
a
exam
join.
record. So that's a join already. So that's a join to combine the two tables. But where it gets interesting is the necessary, right? So the second condition says that the exam grade is equal to the subquery that finds the best grade the student has ever got. Right.
Yeah,
So
so sorry, just to sort of do it bottom up, right?
yeah.
I'm sure I'm understanding this. Here's the problem, which is we have students, we have courses, and we have for each course a bunch of grades. And we want to find the pair of for each student, I want to know their name and the
Mhm.
name of the course where they got the best grade. So the
Right.
first thing I'll do is for each student, I can compute which course did they get the best. No, okay,
So
the inquiry is like,
the
which
first
is the best grade I got?
yeah, what's the best grade I got? And then we go look for which course they got that grade in.
Right.
So better way to write this, I think you could have done this just with a drawing, but this is their example for example purposes.
This
Right.
is
Right.
kind of interesting because, when I think of joins, I would write what probably SQL generates, which is one big join, which just puts all the constraints in a bag and says, like, it has to be your best grade and it has to be from this course, like, all at once.
Yeah.
Whereas humans who write for loops and stuff in, like, C are used to writing these loops which, like, gradually filter down. And
Yeah.
so
Yeah, I
maybe
was
one of
going
the
to say,
reasons SQL is so successful is that it models like the programmer's brain in how they write things down and then translates it to this very efficient relational, like constraint based programming.
yeah, Oliver, I was going to say this is totally not what I would do, and I would
Exactly,
also
right?
point out that you work on query optimization also, so
Yes.
you know the right way to write this, right? What I would do is like what this is doing essentially, as I see it, is like first find me the best grade I've ever gotten, then find me the pair of the name of the class where I got that best grade.
Mhm.
Easy done. That's two loops. Definitely not a great way to do it. If there is a more optimized way to do this, right?
Yeah. Yeah, but really
So what is
the idea is that when we write programs, we have helper functions, and then when we write queries, we have helper queries, right? It's uh, the really simple principle of programming. So we can't just write one single function, that does everything for a program, right? That's the
exactly?
thing you can do when writing a program. Same with query, right? You don't want to write one single pseudo query. Instead, you want to break it down into little pieces, and then
Right.
the
Right.
way for a programmer to do that is that they use subqueries, or there's also things called views. So views are basically variables for SQL, right?
I see.
So break
But
this down. Yeah.
could you give us the intuition of how this can be turned into a join? Which
Uh,
is, two steps of like first let me find the class where I got the best grade. And then second, let me find the names of the classes where I got that best grade from.
Yeah, so on the spot,
Oh, okay.
sure, I can do this.
Do they put this in the paper actually?
Yeah, so they do. They basically have the example in SQL. They have an example of the nested query that uses only joins.
Okay.
So yeah, so I guess I don't want to waste time just trying to figure out.
Yeah. Yeah.
Yeah, I don't have it
But
on the.
the cool thing about the join is you can basically take these two for loops over the table
Yeah,
and turn them into one sort of more efficient scan of the tables that you're working with.
yeah.
I don't know
So
if it's actually just one scan.
to be precise, any query you write that uses subqueries can be turned into another query you write using joins instead of subqueries.
Right. And it's more efficient because you have to scan the tables fewer times.
Yeah. So really, I think a couple database systems do implement subqueries, and the way they do it is that they run the subquery per row on the outside table. So for
Oof.
this, we have a subquery uh, on the outside table, which is student table and the exam table. So for everything that gets past the first condition in the outside table, we run the subquery one more time,
Wait a
right?
I
sec.
see.
When did this paper come out? It seems that I would have thought that we knew how to unnest arbitrary queries for many years now, but it seems recent.
It's pretty recent because people could unnest certain queries, but not arbitrary queries.
So that's the really interesting thing about databases research is that two fundamental things that like I think of as like very foundational are generic join because it's like worst case optimal, which we'll get to later,
Yeah.
and this like query composition thing, which we were doing like some of, but not arbitrary queries. And they're both pretty recent, right? Like we didn't figure out generic join till like 2012 or something.
Yeah, until 2013, around 2013. So that was
Yeah.
about
And it's a
so
huge breakthrough that like nobody's using in real database systems now. And so maybe it's a good transition into
yeah.
Remy's work, the
Yeah,
history of
tell us.
joins,
Yeah.
and like why joins are so cool and good and better than what you could write by hand.
All right.
Yeah, so maybe starting with the early join algorithms like binary join and working our way up to generic join and free join and stuff like that.
Sounds good. Yeah. Um yeah, so when Carl first proposed the relational model, there were two concrete things. One was a relational calculus, one was a relational calculus, one was a relational algebra. So the binary join came out of the algebra as an operator, as an algebra operator, right? Uh, and it's nice because it's really compositional, right? So if you want to join a bunch of tables, you just join two at a time. So it's like when we want to add up a bunch of numbers, we have the binary plus, we add up two at a time.
Right.
So that's nice. So you can just implement this one single operator and then chain it together to combine multiple tables together. So so that was the inception, and then in between that and what's this almo join, there were multiple so-called multi-way join algorithms or multi-way join implementations. So what a multi-way join is exactly what it sounds like. So instead of the join operator only taking two relations, you can take multiple relations. So can you put it down here? Yeah, thank you.
Can we
Sorry, I
really
got
quick interrupt and define what the output of the join is? I think James is asking a question here, which is makes a valid point, which we have circled around it, but like, what does the join compute given a query into n tables?
yeah. So the join, um, I'm gonna go the standard way, right? I have
Okay.
my, but just for convenience, I'll go the standard way. So the binary join operator takes in two tables and a condition about attributes, the columns of the table. So one example is that we want to take student records from the student table, course record from the course table, and then the condition says that the student ID in the student table should match the course record in the student ID in the course table. So the condition is that s.id equals to c.id, right? So it takes in these three inputs, two tables and a condition, and returns all tuples from each table that satisfy the condition. And then for each pair of one tuple from table A and table B, it kind of concatenates the table together to become one single tuple.
So it takes like in a basic way, you can think of it as product and filter. Like take two tables, compute all the combinations of rows between the two tables, and then
Yeah.
filter them down with the condition. But binary
Mhm.
join obviously doesn't it do it that way. It tries to do it in a faster way than just actually materializing all the entire Cartesian product.
Yeah. Yeah, and then another pretty cool blog. Uh let me yeah, it's called Drawing 13 Ways. So there are actually 13 different ways to look at a drawing. Uh and then I'll just go over the table of contents. I said a drawing is a lookup, a drawing is a nested loop over rows, a drawing is a nested loop over columns, a drawing is a compatible alternate realities, a drawing is a flat map, a drawing is a solution to the n+1
A
problem.
join is a join.
It's all over there.
Oh, let's try. Yeah, I came across this algorithm. This is a really nice and concise, like, well, it's not concise, but it is a nice explanation of like the expressive power of joins. It's worth reading.
Very
Yeah,
cool.
so answer to what's a drawing.
Okay, we know
Um,
what a join is now. Good job, Remy. Very good. Now, how do we do it very fast? We did
okay,
binary join, and binary
right.
join was like, okay.
Yeah, so actually just maybe this will also help you understand the semantics. Is that one way to implement a binary join, so you have two tables and then you want to join them. So let's focus on the so-called equi-join. So equi-join means that your condition is an equality or a bunch of equalities. And just to keep it simple, let's just say that your condition is one single equality between one column from table one and one column from table two. Right. So one way to implement this equi-join on these columns is that you build a hash table on the table on the right, where the hash keys are the column you want to join on. And then you iterate over every tuple in the left table and take that column and then probe the hash map of the other table to see that if you can find an entry. Right. So if you can find an entry, then you found a match. You found a pair of tuple that satisfy condition. Output it. So that's the so-called hash join. Right.
So I think the
Uh,
Right.
theme of this conversation is like using cool data structures to make it a bit faster and like
yeah,
planning ahead on what you're gonna do. So the
that's
planning
right.
ahead part was making a hash table for like one of the tables as you scan the other.
That's right.
Right.
So that
I want to repeat this to make sure I understood this. Going back to our original like owners who leash their dogs example. First of all, is that a join? This like
uh
QXZ or Y.
join. That's point of the ownership and then the what the dog wears table.
Right. So going back to your example of like how to implement it efficiently, what you would do is like you go look at the table of all of the people who own dogs, and
Hmm.
you would hash the column that is dogs. Like,
Yep.
so we have a table that maps people to dogs, and you go and create a new hash map that contains what? Like a mapping from dogs to people. So it's like an inverse map for the
Yes.
original table.
How do so you only have to create hash map for one table. So let's just for simplicity say that you have an owning table, you have a wearing table, right? So what a dog wears, maybe it wears a jacket, it wears a leash, it wears a comb or something.
Sure.
So I just suppose that we're gonna build the hash map on the wearing table. Right. So we say that the key is the dog's name or the dog's ID,
Yeah.
their microchip ID, and then we map the every ID to whatever the dog wears.
Or what multiple things it wears in general.
Multiple things wears. That's
Right.
right. Yeah. And then on the other hand, we just have this flat table of people owning dogs. and then we iterate over every single ownership pair, and then look at the the microchip ID that's stored in this table. Look it up in the other table, and then you might find multiple matches because the hash match is gonna map one single doc to an array of things it wears. So when you find more than one thing it wears, you're gonna iterate over everything to
Yes.
to
The hash map essentially gives you off-one access to the data, as opposed to what we were doing originally with the binary join, which is for each person, when I get a dog ID, the microchip ID, I go in and scan the table and get that information out,
yeah, that's right.
all of the leashes. Right. So
Yeah.
the efficiency comes from pre-computing this data structure. And so is this the best we can do? Like, is this the optimal thing to do? To
No,
compute?
so yeah, just within binary join, so building a hash table and programming it is actually pretty, cache unfriendly, right? So in many cases, especially when we have, um, uh, well, let me just talk about, so that was the hash one, and the other popular binary join implementation is the so-called merge sort join or sort merge join. I can never remember which one. Yeah. So the idea is that instead of building hash map, another way we can kind of align the tables is by sorting them. So this
Hmm.
as have an ordering on the values we store, which is pretty natural. We can define comparisons for strings, for numbers, etc. Right. So the idea is that first we're gonna sort both tables. So now there's already a trade-off, right? So the hash map only needs to build hash for one table. Now we need to sort both tables. So there can be a trade-off because maybe the tables are already sorted. This happens when you have a timestamp, right? The new record you receive is gonna be later than the existing record, so maybe it's already sorted. In which case, that using merge sort join is actually gonna be beneficial because you save the time from building hash, right? And then another nice property is that for merge sort, your output is gonna come out sorted, right? So you sort both tables and then you just merge them on the column uh, uh, using the merge step in the merge sort algorithm. So that means that your output is gonna come out sorted, which means that if you want to join the output with another table, you don't have to resort the output. So there's kind of an amortization of the sorting cost.
Right.
So that's just for binary join. And then so for multi-way join, people realize that sometimes we're looking at multiple tables together, and then there isn't a strict ordering of okay, so I should always probe this table first and probe this other table first, and then there's also IO accesses, etc., etc. So really the main motivation to invent traditional multi-way joins was to remedy to reduce IO access. So that part I'm not an expert in, but really that's the high level picture of the motivation. So the limitation of traditional multi-way join is that usually it requires you can join multiple tables, but usually it requires that you're joining them on kind of the same column, right? So imagine you have a movie table, you have a person table, and then you have maybe like some other product table. You always have to join them on some person ID column.
Hmm.
So only some queries can be compiled down to a multi-way join
Classic,
execution. Yeah, okay.
right? So it's not it's not very general.
Right.
Uh,
Because you
so
can always fall back to repeated binary joins. I guess
that
this, yeah, okay. So this
that's
is, as an optimization, you could do multi-way joins, but their expressivity was quite limited.
yeah. Yeah, so really, realistically, in many systems that do support multi-way joins, they always have binary join support as well. So they're gonna have a hybrid plan, execution plan. So plan is the database word uh, IR or intermediate representation. So it's the instruction or assembly code is the instruction we give to the database about how to execute things. Okay, So that's binary join and multi-binary join. So the next stop that we're gonna talk about is versus normal join, right? Um, so what that means is that like in the name there's versus optimal. So what does that mean? It's a little bit of a confusing term. And I heard that Donald Truth heard after hearing this talk, he was asking speaker, what do you mean like your algorithm is worst case optimal? Like it's also is it optimal even in the worst case? Like what does that even mean? So what it means is that um you have your query and you have some data, right? And then we want to know that. So if you give me the exact data and the exact query, we will know the actual size of the output. You just run the query to compute the actual size, right? So instead of knowing the exact data, we know some constraints on the data. So the simplest constraint is that we know that this table has size n, or this other table has size m. So the worst case in worst small drawing means that if you tell me a query and then you tell me these constraints, what is the biggest possible output size you can get for any table under this constraint given this query?
But it's a little more nuanced than just like n times m times whatever. Like
Correct.
you can
Yeah.
always bound the worst case solution by just like the product of all the sizes of the tables or something like that.
Right. That's a loose bound.
But
Yeah.
there's like a much tighter bound that you can give, and that's what the worst case optimal bound is.
That's right. Yeah. So
Right.
tight is the keyword here. So we can always bound any drawing output by just the Cartesian size of the Cartesian product. But that's not tight because there there might not exist any table that satisfy the constraint that actually output that many rows.
Yeah, you have to
Right.
take into account what the query is, right?
That's right. Yeah. So really the first height bound, we limit the constraint to be cardinality constraint, which is that we only know the size limit to each table. Then there's the so-called AGM bound. So it's named after the three authors, Asteria, Gula, and Marx. And then they derive this tight bound, which says that there is actually always going to be a table that actually outputs this many rows, given this query, given these constraints, right? So that's the so-called worst case bound for these queries. And in the worst case almost a drawing, which says that if your queries only involve drawings, then this algorithm runs in time asymptotically bounded by the worst case output size.
I think
Okay.
at this
Okay.
point I'll just link Remy's
Yeah.
blog post on this topic,
All right.
since it's involved.
Yeah, just to summarize this, because it's a couple of steps to understand what the term worst case optimal join means here.
Yes.
Worst case of a join algorithm, like let's think about a binary join, right? Where one table is size m, the other one is size n. The worst case possible output is that all of the rows in both of the tables match in a cross product. And so the table you get is m times n, right? And so the worst case bound for a join query is always the product of the sizes of all the tables involved. That's a
That's
bound. That's not a good bound. And so what you're
that's
saying is that
a tight bound for binary drawing. So if you just have two tables and you only know that their size is at most n, then all you can say is that their output size is at most n squared. And then there
right,
exist tables that produces n squared output. Right. So
right.
binary join for binary join the Cartesian product is actually a tight bound.
Oh, interesting. So for the binary join, it's actually also the worst case optimal bound,
Yeah, confusingly.
Yeah,
which is confusing, right? Because that's the case you want to teach people with. But
that's
when you
right.
get to the case of three, something interesting happens, which is the join over the first two could potentially yield in a null table, which means that the output of the join could be null as well. So is that the intuition for why you can have a tighter bound, or is it too technical to really get a
Yeah.
simple intuition for
So
it?
I will say the technical term that people can look up. But really, so if your query is acyclic, so just intuitively you can organize the tables in a tree, and then the edges are kind of the joins. I'm hand reading here because is essentially versatile. But if your query is acyclic, then binary join is actually versus optimal.
I
And
see.
that people have stuck with it for so long because many queries in the wild are acyclic. So we didn't need a new algorithm to be versus optimal, right?
Interesting.
So the breakthrough is that for cyclic queries, so when you cannot make the arrange the queries in a query in a tree, then binary join is not versus optimal. And then one simple example is that think about like three relations or maybe just one relation, right? Representing edges in the graph. And they will want to find how many triangles there are in the graph. And suppose that we know that there are n edges in the graph. So the trivial bound says that there can be at most n times n cubed number of triangles in the graph, right? So that's a trivial bound. So this bound is not tight because I'm going to leave this as a challenge to the listener because there can actually only be as many as n⁻³ triangles if you only have n edges, right? So I was kind of debating James about a way to prove this. I think there is an intuitive proof, but I just don't remember it. So if anyone can think of a way to do it, let me know.
Right. But just to finish the summary, which is, this bound, when you can get a tighter bound, the reason the algorithm is called worst case optimal is because its runtime is bounded by that tight bound, right?
Yes.
And so that's where the term worst case optimal comes from. It's the running time in terms of the tightest worst case table bound.
It's when the tables are adversarial, but you're smart about bounding the output.
Right.
It's like the biggest output with bad tables you could get for a particular query.
That's right.
Yeah. This is how you know it was an important result, because it takes like 5 different explanations to really get to what it was, right?
Yeah.
But okay, what does this concretely mean for us, right? It means that like we don't have to do binary joins, or binary joins can actually be exponentially, no, like polyrhythmically, like they can be much worse than what you can do with the smarter way of doing joins.
Right. So theoretically, in the worst case, right? In theory, people talk about worst case complexity. In the worst case, when you have cyclic queries, binary join can run asymptotically worse than worst case optimal join.
I see.
If you have 8 queries, then the theory says that there's no asymptotic differences, but the practice is that there might be a difference.
I see. And so what happened after worst case optimal join was discovered? Did it become the default way people use and implement joins in their databases, or is it still the old way of doing things?
Yeah, so there's to me a bit of a deafening silence that it's been 10 years since was optimal join. There are like 3 or 4 databases who actually implemented it. So what's wrong, right? So why don't people care? So part of the reason was what I mentioned is that lots of the real world queries, they are actually acyclic. And then so people are fine even with asymptotic guarantees, they're fine with binary joins. And then even for cyclic queries, like the keyword is still the worst case, right? So you're not gonna get the worst case data all the time. You're not gonna get the worst case performance all the time. So people maybe like it takes a lot of effort to add one more algorithm to the entire database system. So to build a database, we have to provide many guarantees. We have to be ACID, we have to be maybe parallelize it, we have to be distributed it. So it's a lot of work to implement one more new join algorithm in any database. So really, to convince anything, you need this. We need to really show that this has strong performance benefits or other benefits, right? So one large reason is that like on the real world data, I think people haven't seen enough evidence that worst case optimal join actually makes things faster. And then this can be like in practice, this can be due to engineering, right? So binary join has been optimized for 50 years. So it's been engineering to death. Whereas what's this optimal join is relatively new, right? So it's only proposed 10 years ago, which is a short time span compared to 50 years, right? So it just hasn't been it's like functional programming and imperative programming, right? So there's always a little lag of the performance of FP behind imperative programming. But I think at some critical point, this lag might go away, or there might be other benefits that overweight the negligible performance gap. So I think the same thing might be happening to versus optimal join as well.
Right, and you have some interesting work in this area, Remy.
I
So
think
can
it's,
you
yeah,
talk
free
about?
join time. Free us from our preconceptions about joints and why they are
Let's
different.
let's be free. Yeah. So free join is really practical, right? So as I just said, so I think lots of the reason people don't use optimal join are practical. So they haven't seen that why should I bother implementing a new algorithm? The idea of free join is that we want to say it's not a new algorithm. So we didn't say this explicitly in the paper, but I think in my blog post, I have a blog post trying to convey that your database already implements something close to free join. And what free join is a unification and generalization of binary join and versus optimal join. So we're really trying to make the case that they're not that different anyways. So don't be scared to improve your database system so that it can be implementing both binary join and versus optimal join.
Yeah. So what is the crux of the free join idea here?
Yeah. So at a very high level, so right, so the name says free, right? So what are we freeing ourselves from? So in binary join, the constraint is that we're always processing two tables at a time. And then every time we join two tables, we're going to join on all join attributes, all shared attributes between the tables. Right. So I have this picture where one axis is the number of tables you join, one axis is the number of attributes you process. So binary join is one extreme where you process only two tables at a time and all attribute between two tables at every step. Versus optimal join, or the concrete sense, which is generic join, is at the other extreme. You only process one single attribute at a time, and then you're gonna bring in all tables that join on at that attribute, right? So those are really two extreme points in the design space of join algorithms. So free join covers the entire design space by saying that we are allowed to decide and choose how many relations you want to process at each step, and then how many attributes from these relations you want to process at each step. So in a sense that if you tell me, oh, I'm gonna do one attribute at a time, and then I'm gonna do all relations at a time, you get generic join or versus optimal join from free join. So you instantiate free join into versus optimal join. If you tell me that I want to do two joins at a time, and then all attribute at this time, then you get binary join back. And the important point is that besides representing these two extreme points, we can also represent points that's not covered by either algorithm. And it's possible and likely that these points in the middle of the space is a bit better performance than either of the extremes. So that's the higher level idea.
Yeah,
Remy,
it almost feels like, sorry, Oliver,
no, you go, you go.
please. Yeah, I was just thinking this, the way you're describing it, it almost feels like a little machine where you feed in some parameters, and the machine is actually capable of giving you existing algorithms like the binary join and sort of worst case optimal join. But
Right.
if you give it new parameters, it can give you algorithms that make different trade-offs that lie in the spectrum between these two algorithms, the binary join and the generic join algorithms. And
That's
so
right.
the thing that I find really cool about this is it's sort of mechanizing the insight between these two algorithms and the design space, right? And it allows you to sort of turn the crank and get new algorithms out. And of course, from a maintainability perspective, you're arguing that if you implement just this one algorithm, you get both generic join and you get sort of the standard binary join from your little machine, and you can then experiment with other kinds of join algorithms. Maybe you're running your queries and you're like, let me try the parameter 5. I don't know what 5 is here, but like let me just try 5 and see if it's better for some reason, right, in the
Right.
background. And if that turns out to be true, that's what you ship the next release or something like that.
Yeah. Yeah. So that's exactly the idea, which is that people are scared, they don't want to implement one more algorithm. I'm telling them that you don't need to add algorithm. So you can replace your existing one with this one. So it's still one algorithm in your system. And then it's actually not gonna be that hard to change it into FreeJoin. So in the blog post, I talk about, if you implement late materialization, you have a little bit of dynamism in your query execution, then you can get FreeJoin pretty easily. I think I never built, a commercial database, but I try to make the case saying that yes, you can slowly massage your existing binary join implementation to at least take some ideas from FreeJoin. And then
That's
yeah,
very neat, and I think like a unified framework for talking about all these join algorithms is very cool. But it brings
mhm,
up a problem which I was about to ask, and then James asked in the chat, which is that what does this mean for query optimization? Like we've been thinking about query optimization for the old join algorithms for so long.
right.
Do we need a completely different way to optimize queries? And like, does it make it harder to have this larger space of queries that you can generate?
That's right. Yeah. So I think I have two answers. The answer in the paper is that we're being practical, which means that uh, it's an honest answer. I optimizing for other things,
Yeah.
but we're being practical, which is that uh, we just reuse the existing optimizer from existing database engine, and then on top of that, we greedily optimize the plan so that we always guarantee we never to make it slower, right? So
So
our
the
yeah,
paper's proposal is reuse your existing algorithm and write a small algorithm on top that tries to improve things a little more.
correct. Yes. So I think that's a nice first step, which is that you if you want to just want to experiment, just want to play with FreeJoin, then you don't have to throw away your existing optimizer. So the other answer is that yes, because we're representing a larger space, the optimizer now also needs to explore a larger space. So in that sense, it does make the optimization harder, but really you don't, you could just you could just exploring the space you usually explore, right? You don't have to explore the entire space. So if you want to explore it, you might find better plans, right? So you have the freedom to decide, right? Do you want to just be conservative and then use our greedy optimization to make it faster, or do you want to be a more aggressive and better explore the search space?
Very cool.
Yeah, there's the profound trade-off in optimization, right? Where like more freedom is not always a good thing. Sometimes it's really bad because it makes your search problem blow up and you can't do any optimization now. But I
Right.
like the point, like you can make the same choices, right? You can just say, I have my free join implementation and it is a free join implementation, but really I'm only going to expose you with three parameters. One is like the standard binary join, the other one is the standard worst case optimal join, and one is something in the middle. And that's the
Mhm.
only three optimization parameters you can use. You don't get the full flexibility of the continuous sort of this like machine I was talking about that cranks out new algorithms for you. And that
Right.
is way to limit it. But one place I think the flexibility is actually useful is that if you have other constraints in your optimization system
Mhm.
that constrain the space of possible outputs in the spectrum of the algorithm, that
Mhm.
still gives you a fewer number of points, but those are dynamically constrained by your optimization problem, as opposed to like you pre-committing to some set of points that are useful. I don't know if that point really made sense, but sometimes like the thing that constrains your optimization space is, other constraints. And so if you have enough of those floating around and you have clever ways of linking them to how the join algorithm needs to operate,
Right.
then you can have a smaller space. For example, one of this is like if you needed to do a distributed query and
Mhm.
some data has a set of columns on one machine and some other set of columns on another machine, then you
Mhm.
know that like the only valid parameter for the number of columns to compute with is one, two, or three, right? You don't have
Right.
to even worry about four and five. And so like those
Yeah.
kinds of constraints can really help you limit the space while retaining the flexibility that the algorithm has.
Yeah, so this is actually already known in binary tree optimization. So one example is that if you know you have a very small table, so that's already one constraint. That's called cardinality constraint. And even if the table is itself is not null, not small, right? So if you know that this predicate is gonna return very few rows, then you probably want to process that first because that filters down the results better. So you will know that by keeping statistics from the data. Right. So for example, if you have a selection that's a range selection, and then you have a histogram of your data, then if the range is to the tail of the histogram, then you're gonna know that, oh, this selection is not gonna return many rows. Then I'm gonna run it first so that I throw away data as soon as possible. So yeah, so optimizer absolutely use these kind of statistics and information to guide the exploration of the search space.
Cool.
Neat.
I
So
think
this might be a good time to wrap up with like ending thoughts and questions, maybe the history or future, sorry, not history, of
give
join
us
algorithms. Like what's next? What are you excited about working on? And then we'll do like a wrap up question we always asked.
Yeah, so what am I excited? I'm excited about a bunch of things. So I think I'm here at Simon's. So one reason I'm here is that there are lots of really excellent theory people here. And then one recent trend in databases is that there has been a breakthrough in many uh, uh, areas of optimal algorithms, such as the vortex-optimal join. So vortex-optimal join only supports joins, but we have other queries like selection. We have union. We have differences. So there has been a string of recent work making vortex-optimal algorithms that incorporate these more expressive algorithms, right? And then so I think it's I like to look at the theory people's work and then put it into practice. So one thing I'm really excited about doing is how can we take this theoretical algorithm and do the same thing we did with free join. So put them into practice, put them into testing practice, and see if they are actually going to be useful, and then see if it's actually worthwhile to adopt them in practice, right?
Yeah, so
Um,
making the theoretical more practical in the same way that you did with free join.
right. Yeah. Yeah, and actually, I have a list I made on my website, kind of
Is
mostly
it your
for
hit list?
it's my hit list. Yeah, it's not quite hit list in itself research project, but it's kind of a small sampling of the topics the flavor of topics I'm interested in, and then for people who are interested, I think if you want to work on these, some are research, some are not, some are just practice. Let me know. I think these are all the things I love to work on in the future.
sweet.
It also looks like from your website you're going to be looking for students soon as you start at UCLA. So
Yeah,
uh,
so I'm looking for student right now. So if you think you can do some of these, try to do it. If it works, or if you try hard enough and see problems, let me know. I love to work with you for the long term.
cool.
Sweet. I think for the wrap-up question, we usually go with what are some of the things that you've enjoyed reading or like listening to or watching? And this doesn't have to necessarily be databases related. This can be just sort of greenfield, whatever you enjoyed doing recently.
Yeah, so uh, I'm gonna take it easy way out to tell you the most recent paper I read, which is this paper by Yeting Ge and Leo Dimura. Actually, it's a PL paper. So it's about the algorithm for quantified elimination in Z3. So the paper is called, I think, which is a complete decision procedure or something. Complete instantiation for quantified formulas in SMT. So I'll post the link here. And it's kind of the first time I really understand how quantifiers work in Z3, and it's actually way more powerful than I thought. And the reason that I look into this is that I've been obsessed with the problem of verifying SQL equivalence. So give me two,
Oh,
can I tell you that they compute the same result for databases or not, right? So this requires a lot of quantified reasonings. And then until this, I thought it was not possible purely in Z3. But now I think there might be a chance to kind of involve. So because like lots of reasoning involve rewrite rules. The rewrite rules are basically quantified
I
formulas.
also know that Vampire does crazy stuff with quantifiers. That's like the extent of my knowledge about Vampire.
Yeah, so I think Vampire is a lot of rewriting driven. So in Z3 it's actually a lot of model driven. So able
Ah,
in instantiate the quantified variable with a concrete term or concrete value. So this is important because when it is satisfiable, it needs to return a model, right? So
right.
it can, okay, my rewrite rule failed. I actually need to give you a counterexample of why, your theorem is not true. Um, so yeah, so I think that's the cool thing about this paper.
Interesting. Yeah.
Sweet.
Okay.
Well, thanks for coming to the stream today, Remy. It was great chatting with you. There's like a billion other questions we would love to ask you, but we don't want to keep you for over 2 hours.
Thanks.
Um,
It's been super fun.
yeah, but hope you enjoyed this. Yeah, I think we're planning to return in 2 weeks, but we might have to cancel in case I have some stuff to go through.
Yeah.
All right.
2 weeks. We'll go forward definitely in September,
Yeah.
I think.